The discriminant is a particular part of the quadratic formula that is really helpful in helping us sketch a parabola, and it also has future applications that you'll look at, but it particularly will tell us how many times or how many unique solutions or x-intercepts that we will have when we sketch a parabola. So here we already know that we've got in the quadratic formula we've got this negative b on 2a, which is what we call the axis of symmetry. Now this is a vertical line, and we know that's where if we sub that value in, that'll be the x-coordinate of the vertex. But what else is in the quadratic formula? We have what's under this square root here. Okay, so we have b squared minus 4ac, and that is the discriminant. Okay, and we can denote that by using a triangle. So if I were to actually write that over here on the left, with the triangle, the discriminant is equal to b squared minus 4ac, okay? And let's look at three separate cases. So here, the very first case that we're going to look at is when the discriminant, or b squared minus 4ac, when I put in those values, is greater than 0. Now, I should actually backtrack and say that for the quadratic formula and for the b squared minus 4ac, the parabola must be in the form axy equals ax squared plus bx plus c. Now, the other two cases are when, if I were to have the discriminant equaling 0, okay, when I subbed in the values for a, b, and c, and I actually got 0, okay, and the third case is when I sub in those values of a, b, and c into this equation here, and I actually get a negative number. Okay, so here when the discriminant is greater than 0, so that's when my answer is positive. Okay, I'm actually going to get two unique solutions. Okay, so that means I have two distinct x-intercepts. So that could look something like this on the graph. Okay, I'm going to have a point here and a point here. Now, they're not the same. They're clearly different points. Now, when I sub in values for b, a, and c, and I actually get an answer of 0, okay, for the second case, then I'm actually going to get, I still would technically get two answers, but the answer is going to be the same. So I'll only have one unique solution. So in this case, often it will be a bounce off the x-axis. So I might have something like this, okay, where it is only touching the x-axis at one specific point. All right, and the last example is when we have the discriminant, when we sub in those values, and we actually get a negative number. Okay, now when it's negative, that actually means that it's going to be completely above or below the x-axis. There will be no x-intercepts. Okay, if you actually put that in the quadratic formula in your calculator, it would come up with an error. So, technically you can solve it, but not in the real number system. Okay, so it could look something like this. Okay, or it could look something completely below like this. Okay, so there is no x-intercepts. So that's the discriminant, okay? So I might just pick an example to run through just so we could have a quick look at what one would look like. So here if I had, say, y is equal to x squared plus 5x, oh no, I might go 6x plus 5, okay? Here my values of a is 1, b is positive 6, and c is 5. So I've got the discriminant as b squared minus 4ac. Subbing in those values, I get 6 squared minus 4 times 1 times 5. So this would be 36 minus 20, which equals positive 16. Now, at this point here, I would say the discriminant is greater than 0, so therefore there will be two unique solutions, which means that I'll have two unique x-intercepts. Okay, so if I had another example, say y is equal to x squared negative 8x plus 16, okay, I had values of a is 1, b of negative 8, and c of 16. Alright, so here I'll put this into the discriminant formula, which is a part of the quadratic formula, b squared minus 4ac. I sub in the values that I have from my equation, so I have negative 8 all squared minus 4 times 1 for a times 16. So that would be 64 minus 64, and we get exactly 0. So in this case, I would actually get two solutions, but only one unique solution. Okay, so this means that I'd get one x-intercept. Now, I could actually rewrite this equation as y equals x minus 4 all squared, which I know as a shift to the right by 4. And if I was to sketch this on the graph, it would look something, apologies about my axes, something like this, okay? Where here, this would be 4, 0. Okay, so it's only hitting the x-axis once. Now, if I had something else, say, in example 3 here, if I had, say, y is equal to x squared minus 6x, and then I'd have plus 10. Here I'd have a value of 1, a b value of negative 6, and a c value of 10. Putting this into the discriminant formula of b squared minus 4ac, I'll sub in my values, so I'll get negative 6 all squared minus 4 times 1 times 10. Here this would be 36 minus 40, and you can gather that this would be a negative answer. So the discriminant is less than 0. So this one here would actually be completely above or completely below. So here we would say no real solutions. And that means no x-intercepts. Now, I know that if I could actually, by completing the square, I could actually write this as, well, this is one way to actually write it. Y equals x squared minus 6x plus 9 plus 1. Here I can actually know that that is x minus 3 all squared plus 1. And then this is in vertex form with a vertex at positive 3 and 1. And because it's a positive x squared of 1 out the front there, I know that this would actually be, apologies about my axes, something like, if this is 3, 1, okay, it would be something like this. And you can clearly see that there is no x-intercepts there. So that's how you can use the discriminant to let you know how many x-intercepts you're going to have, how many unique solutions you will have.